Welcome back, everybody. Transformations, lesson 3. We're looking at reflections, and we're actually going to look at lesson 3 and 4 in this assignment. First of all, so we should be on this page in your workbook, and the first thing we're going to look at is something called invariant points. Now, just as the word implies, invariant points, the word vary is in there. If something varies, it changes. So invariant means it doesn't change. Invariant points are points on a graph which do not move after a transformation. So we're only bringing these up now because the first topic we did was translations. Any graph that moves left, right, up, down, all points are going to move on the graph. But with reflections, there's potential to have invariant points. Now, for the sake of time, we're going to skip the investigation part of this lesson, and we're going to go to page 92. If you guys could please find that page. Okay, now we are going to look at, this is basically the summary of the investigation that was discovered in the previous few pages. A reflection is a transformation which reflects or flips a figure about a line. And we're going to fill in these blanks to kind of summarize the investigations. So if we're reflecting in the x-axis, okay, if the graph of y equals f of x is reflected in the x-axis, then it is the graph of, and they're looking for what the equation becomes. Now let's go over here and just take a look at the graph to figure this out. Okay, so this, say we have a point, say here, on the original graph, okay, at x comma y. Now, if that point is reflected in the x-axis, it's going to go somewhere down here, right? Now, what would change as far as a coordinate? Would the x value change or would the y value change? Well, the y value would become exactly the opposite, so negative. So in other words, if you then replace y with negative y in the equation, then our equation would become negative y equals f of x, or divide both sides by negative 1, okay, it would become y equals negative f of x. You do not divide inside the function, this x inside the function, that's not okay, can't go inside the function. So the negative basically is in front of f of x, that's essentially replacing y with negative y, and therefore a reflection in the x-axis. So to summarize over here, it is the graph of y equals negative f of x. Okay, let's look at the next one. Reflection in the y-axis. Okay, so let's once again take a point on our original graph, say here, at x comma y, and if we reflect it in the y-axis, okay, over to here, if you'll notice, y will stay the same this time, but x will change sign. So if this was at positive 3 for x, it would now be at negative 3. Okay, so in the equation, the replacement would be that x gets replaced with negative x. So x inside the function gets scooped out and replaced with negative x. Okay, so we can summarize that down here. Now back to the this part. If the graph of y equals f of x is reflected in the y-axis, then it is the graph of y equals f at negative x. Okay, so just think, if I'm reflecting in the y-axis, x is changing sign, and therefore you replace x with negative x. Okay, our third reflection we're going to look at, or summarize here, is the reflection in the line y equals x. Now whoops, sorry about that. We have looked at that already in our last unit on functions. That essentially is an inverse if we reflect in the line y equals x. So if the graph of y equals f of x is reflected in the line y equals x, see that line drawn on this graph here? Okay, then it is the graph of, now think back to inverses from the functions unit. To find the inverse, we switch x and y. Okay, so if we switch x and y in our equation, y equals f of x, just scoot down here for a minute, x will be equal to f at y. So x and y switched in this original equation. Y became x became y. So it would be the graph of x equals f at y. Okay, and then the function notation version of that, if our inverse was a function, we would use the notation y equals f to the negative 1 of x. Okay, so if we look at kind of the transformation here, let's say this point was at, well, we'll keep it generic, x comma y, and it reflects over this line, it would now become y comma x. Or, to use some numbers, just to make it look a little more realistic here, let's say it was at 3 comma 2, then on the inverse graph it would be at 2 comma 3. Okay, so those are our 3 reflections. We're going to look at applying them now to some examples. Okay, example number 1. The graph of y equals f of x is shown. Sketch y equals negative f of x. So what do you notice here? That was the situation where y was replaced with negative y in order to end up with the negative in front of the f of x. So that would be a reflection. Let's see, if y goes negative, that would mean that the point would end up, okay, so reflection over the x-axis. Okay, so that means each one of these points is going to get reflected over the x-axis. So this point here at negative 4 comma 6 would now be at negative 4 comma negative 6 down here. Okay, so pause your video and you guys go ahead and plot all the new points on the reflected graph, okay? Just for part A, and then check back. Okay, let's compare our graphs. So you'll notice negative 4, negative 4, 6 went to negative 4, negative 6, and basically all our y coordinates went to the opposite sign, 7, negative 3, 7, positive 3. Now, there were 3 points on here that actually didn't change. And it kind of makes sense, because if y changes sign and y is already 0, then 0, negative 0 is still 0, right? So these 3 points did not change. Those points are called invariant points. Okay, notice where they are. They're on the x-axis. Where were we reflecting? Over the x-axis. Okay, let's take a look at part B. So we have f at negative x. So first notice what's different. Instead of y equals f at x, we have y equals f at negative x. So that means x was replaced with negative x, and therefore it would be a reflection over the y-axis this time. So imagine an x-coordinate changing sign, it would land over here. So you guys go ahead and do part B, pause your video, and we'll see if we get the same equations. And what I would like you, or the same graph, I mean, I'd like you to circle the invariant point as well, or points, if there's more than one. Okay, pause your video. Okay, hopefully our graphs look the same. You can see how it's been a reflection over the y-axis, but each point, also the x-coordinate changed sign, and therefore negative 4 and positive 6 would be now at positive 4, positive 6. All right, now the invariant point is right here. The point that did not move from one transformation to the next is still at 0, 4. Notice where it is. It's on the y-axis. What did we reflect over? The y-axis. Makes sense it didn't move, right? Okay, let's look at our last part of this example. Okay, let's look at the equation, and you'll notice our equation now is x equals f at y instead of y equals f of x. So what happened? X and y switched, and that we know is the inverse, okay, inverse, and in particular it's a reflection, graphically I should say, a reflection over the line y equals x. Now, these can be a little tricky if you actually literally try to reflect it over that line. It will look right once we're done, but what I would recommend is we take each one of these points, so negative 5, 0, and then on the inverse, that point would become 0, negative 5. Okay, so this point here would now be 0 and negative 5, so down here. Okay, so you guys do that with the rest of these points, and then we'll compare our graphs. And again, circle what you think would be the invariant point or points. Pause your video. Okay, this one was a little trickier, wasn't it? And a little trickier to draw. Okay, sorry about that. Okay, so it's probably a good idea to write down these points just so that you can plot them. And I would work in order from left to right when you do this, so that each time you plot a point, you connect it from the last point that you drew, and then you won't get mixed up. Okay, now let's look at this. I drew the line y equals x on there in red to get a visual representation of whether this is a reflection in that line. Oh, and to draw that line, it's just simply a line that goes through for every, you know, when x is 5, y is 5. When x is 10, y is 10. That's that line. Okay, now if you look, the blue graph does appear to be a reflection. This piece here was reflected from here. This piece here reflected over to this piece here. So it does look right. Now let's talk about invariant points. Okay, so with our last two, we noticed the invariant points occurred on the line about which we were reflecting. So using that same theory, then here's our line of reflection, and the graph crosses right here. So that should be an invariant point. Notice the coordinates of that point, 2, 2. When you find the inverse, or you reflect, it would switch x and y, and you'd still be 2, 2. Now what about these points? Because these also seem to have not changed, right? Like, did 0, 4, did that point not change? Because there's still a point there, right? And the question would be, no, it did change. 0, 4 ended up plotting here. Just so happens that we also had a point at 4, 0 that ended up at 0, 4. So that point did change. It's just another point replaced it. So it looks like there's still a point there. There is still a point there. Okay, so moral of the story is the invariant points are on the line of reflection. Let's just make a note of that because that's important. Invariant points are on the line of reflection, where the graph crosses the line of reflection. So if the graph does not cross the line of reflection, you won't have any invariant points. Okay, let's look at the next example. The graph drawn is in the thick line is a reflection of the graph drawn in the thin line. So we start with thin, it goes to thick. Write an equation for each graph drawn in the thick line. So we need to first of all look at the graph and figure out what kind of reflection happened. We have 3 to work with, in the x-axis, y-axis, or in the line y equals x. So take a look at A. Okay, if it reflected over the x-axis, that means this point on the x-axis would still be on the other graph. It's not. If it reflected over the y-axis, this point on the y-axis is a point that wouldn't have changed, invariant point. So it looks like our third option on the line y equals x, here's the line y equals x. See how that point didn't change? That means this was a reflection in the line y equals x. Okay, now they want the equation. Yes, you need to still write this description down because it helps you get the next step. The replacement would be that x and y, x goes to y and y goes to x. So in our equation, here it is, y becomes x and x becomes y. And there we go. Now, is our reflected graph, a function? Does a vertical line only pass through that thick line once? Yes, it does. So we could also write this as y equals f to the negative 1 of x. And that would be acceptable as well. Okay, you guys pause the video and try B and C, and then we'll see if we got the same answer. Okay, to quickly finish this first part 1 video, part B, reflect over the y-axis, invariant points on the y-axis, x gets replaced with negative x, hence here's our equation, and this one, invariant point on the x-axis, therefore reflect in the x-axis, y goes to negative 1, we could have this version or this version. All right, see you guys in part 2 for this lesson.